considering axiom systems A1 and A2, and some set of functions on either system, some set of operations, and how those operations overlap with each other. When two operations overlap, when they overlap, we're left with the ending result of what do you do when their singularity is reached, when there's only one object left. And so what do we do when f of a1 doesn't equal f of a2 and f of a1 equals f of a2? The edge case of the not equals operator in resonance theory. The not equals operator assumes that there is the possibility in the world of physics, or in terms of entropy, that these two will actually be the same. And when I refer to, what do I want to say next? I should be able to do this. It shouldn't be that bad. So for the end result of tossing out the false by f of delta doesn't equal f of delta, when delta is type set and it's of type object, JECT, then delta doesn't equal delta except for the edge case that delta equals 0, or the two objects are the same, in which case I would have f of delta 1 equals f of delta 1 with delta 2. Now f of delta 1 equals f of delta 1. Okay, but this has type delta, so this is delta equals f of delta 1 equals f of delta 1. Brackets. Bracketeering. I hear you start with the fewest number of assumptions as possible. Objects overlapping is more assumptions. So fewer assumptions on objects would be that objects exist independently and that intersections have to be proven. This expression freaks me out, how delta can be an aspect of some type in a situation and then output another delta, because deltas are just essentially entropy in their most complete form as deltas. So I'm assuming that these operations in here are inherently, the deltas don't equal each other. So I can just write delta. I don't have to write delta sub 1, delta sub 2, or anything like that. The deltas are most likely inherently different. But also for a set of size 1, 1 is an object of size 0. Yeah, 1 is a point object. So what's the delta for 1? When does 1 equal 0? 1 equals 1 leads to 0 when, at least in one direction, no, I can't do 1 goes to 0. I think 0 can't lead to 1, but I'll use the word but. 1 can lead back to 0 as an assumption, a starting assumption. So a set that contains something is, I would say, the smallest instance of a set, because what is a box with no objects in it? So that's the difficult question. So you can't assume, what is an empty set. You have to say, can sets be empty or can't they be empty? So that would be their discord, and that's not a singularity. So this is empty set versus a set that contains delta. Let's see if I can make the entropy just grow on this right here. So if I have a set delta, that can have type delta, or it can have type a box that contains a box that contains a bunch of delta. So in the case that delta equals this expression trapped in brackets, the set here. Yeah, so you have to start out with an empty set. And then I'd have to say the empty set exists. The notion of sets is at discord, but the empty set does exist, and its size is, I think this is an important result right here. So we take the assumption that the empty set is inherently lower discord. if the empty set exists, then it has size of empty set equals 0, implies that empty set equals 0, comma 0 equals 0, the metric on 0 equals a set containing the metric with a 0 in it, which is not necessarily the case. Oh, I did it wrong. I'm reversing operations. What am I doing so wrong here? So really what I need is this notion of a size of entropy. So like entropy as an actual thing that's measurable by outputting some scalar that measures the amount of discord deviation in some respect. So in terms of sets, I think that our entropy would be entropy. No, the number of objects in a set is inherently considered discord because it can take on any range of values. So I imagine in terms of a box, for a box being empty equals 0. And when it contains something, it's defined and it equals something. Another box that contains delta. Boxes can contain other boxes. This is not going on my blog. Boxes can contain other boxes. Boxes over here, over there, and those can contain delta. And if we can recursively show that we've exhausted all of the delta, and we moved the system into resonance, that is singular. So it's a resonance of size 1. I'm measuring the resonance by the number of different objects that are resonating with each other. So right now I have points, and that's a reduction of the set of possibilities in different containers to where there's nothing left in the containers, and all we're left is the discord of a container. And I guess because containers can equal containers, but we could start out computationally by repeatedly removing objects from a box, and then, well, in a truly random world, we might have boxes, but when we reach into a box, we don't know whether we're going to grab a box, the contents of a box, or something outside of the box that's an object. So we have to be able to somehow distinguish the box from the object. And when a box and an object meet at a singularity, the singularity for an object and a box is when the object is too small to have any contents. So we have when the singularity for an object and a box is when box equals this point, we'll call it P, point, I'm writing impermanent again, equals point sub 1, singularity for an object. A box is crushed down to a point, and that point has size 0. Size 0 doesn't have the point though, so maps to. I just gotta pick up what's important now. I'm not sure. So I'm gonna go with my trusted friction pen. Okay, so the singularity for an object and a box are when the box is too small to have any contents, and I think this really messes up my notion of epsilon. So for a single object, some delta on an object, that equals the overlap of two other objects, assuming an object was defined as an independent entity. And yes, objects are inherently separate, and so those independent entities would be two other objects either overlapping or objects not being able to overlap. If both of these things are true, then we have the singularity of when the two objects are just touching. That singularity establishes the validity of the assumptions that guided it down to considering its size being 0, or it being a point in between two different systems whose result was 0. And that's, for some reason, makes them compatible. It's like a fundamental axiom in resonance theory. It is a fundamental axiom, and I see it all over the place, but I would like to know if a 0 doesn't equal a 0. Okay, if that's the case, then that implies 0 doesn't equal 0 implies there's a 0 sub 1 that doesn't equal a 0 sub 2, which implies that 1, by visual relationships, it implies that 1 doesn't equal 2, which is a fine deduction for something that might be inherently wrong. Okay, let me try assuming that 0 equals 0. That implies that 0 of 1 equals 0 of 2, which implies 1 equals 2. But that would be a singularity, or it should be. If you can prove 1 equals 2 by some reasonable deductive system, here's the problem. So this suggests, first off, we have 2 abutting objects. And that's incorrect. Let's go this direction. It should work, I think, in all cases. We'll start out with 2 sets that contain points. One of those points is a 0. 2 separate objects that contain 0. And we have 2 overlapping objects which contain 0. And that leads to the state where the objects are both separate and overlapping. So we see here that discords tend to distribute across, and they also tend to be given any expression that involves a discord. I can establish from that entity's effect on a system. So if I have some function, and I want function to be a super loose notion right here, if I have some function f of delta, and we'll define the map dash r is identical with returns. It's a map that returns something. So if f takes type delta, that implies that delta equals f of delta. So if f of delta returns delta, that implies that f of delta equals delta. Okay, no, I'm wrong. Now I think I have it. If delta equals f of x, that implies, I don't know if I'm right. You know what, the delta should distribute out, not distribute in. So if I have f of delta, so function of discord, delta, returns delta as a function affecting f of delta does not equal delta. And for a function delta on some set delta, or on some mystery thing delta, returns delta of delta equals delta 1 operating on delta 2. That is, since delta 1 doesn't equal delta 2, inherently it's assumed they're different. And that's its discord. But I have not equals. And not equals is separated by the singularity 0. Or it's satisfied by the singularity delta 1 has size 0. This is really bad today. Delta 2 has size 0. But there's probably all sorts of points where this can happen. But here, once again, can I measure the size differently? I'm talking about, the concept of the size of a set. They're both empty sets, and it returns 0. But what validates the integers that come after 0? And I'm not sure. I hear that type is more powerful than the notion of sets in many regards. And types have type compatibility. If I assume that delta 1 does equal delta 2, these both can range, and they're inherently deltas. So by that assertion, so I'm about to quit, but I think the overarching pattern is, if we're going to have functions, there's some function delta that takes delta, that takes delta, that takes delta equals a set of results 0. So it returns 0. Once again, the notion of 0 is blaring in my ear without being able to substantiate it except for everywhere. You know what? The size of 1 equals 0. No, the size of 1 equals 1. The size of 0 equals 1. That's enough of me getting stuff mixed up for now.